You know, every single time you send an email, buy something online, or log into an account, you're relying on digital security. But have you ever stopped to wonder what's actually happening behind the screen? Well, today we're going to pull back that curtain on the invisible world of cryptography and find out about the powerful and surprisingly simple mathematics that keeps our digital lives safe. Think about it this way. Your laptop, your phone, your entire online world, it's all protected by locks. But they're not physical ones made of steel. Nope. They're digital ones, built from pure information. And they're the only thing standing between your private data and, well, everyone else. So what's the big secret? What are they made of? It's not steel, it's not silicon, it's something way more abstract and honestly, way more powerful. The answer is pure mathematics. So deep down, at the very heart of all this security, you've got these incredible mathematical ideas. Let's dig in and see how these abstract concepts create the real, unbreakable codes that protect us every day. The whole science of creating and breaking these secret codes has a name, cryptography. And the toolkit that cryptographers use, it comes from a branch of math called number theory, which is really just the study of whole numbers and all their cool properties. It's all about how numbers relate to each other. So, where do we even begin to build this digital fortress? Well, you start with the most basic, the most fundamental building blocks in all of number theory, prime numbers. These special numbers are the absolute bedrock of modern cryptography. Okay, so quick refresher, what is a prime number? It's just any whole number bigger than 1 that you can only divide evenly by 1 and, you guessed it, itself. Think of numbers like 2, 3, 5, 7, 11. They're basically the indivisible atoms of the number world. This really shows you the key difference, right? Primes, they're like diamonds, fundamental. You can't break them down any further. But other numbers, which we call composite numbers, are more like that brick wall. They're built from smaller pieces. For example, the number 20, well, it isn't prime because you can get there by multiplying 4 and 5. It's this indivisibility of primes that makes them so special. And this is where the magic really happens. A computer can take two absolutely massive prime numbers and multiply them together in a split second. But, and this is the crucial part, if all you have is that giant final number, trying to work backwards to figure out which two original primes made it, that is incredibly, incredibly hard. We're talking time-consuming even for the fastest supercomputers on the planet. This is what we call a one-way function, and it's the absolute core of so much of today's encryption. Okay, so we have our building blocks, our primes. Now we need to figure out the rules of the road, you know? How do different numbers actually interact with each other? It's all about finding out what they have in common, or sometimes what they don't. First up, we have the greatest common divisor, or GCD for short. And the idea is actually super simple. You take any two numbers and you just ask, what's the biggest number that divides into both of them perfectly with no remainder? For 12 and 20, that number is 4. It's the largest piece they both share. Now, finding the GCD for small numbers is easy, but what about the gigantic numbers used in cryptography? That's where this really clever trick comes in, the Euclidean algorithm. It's this super efficient step-by-step process. You basically just divide the bigger number by the smaller one and look at the remainder. Then you do it again with the smaller number and that remainder. You just keep doing that over and over until the remainder hits 0. That last non-zero remainder you got, that's your GCD. It's so simple and elegant, and computers can do it in a flash. Okay, but what happens if two numbers have no common factors besides the number 1? Well, we call them co-prime. Take 14 and 15. They're neighbors, right? But the only thing they have in common is 1. And this property, this idea of being relatively prime, is absolutely essential for creating secure keys that are just impossible to guess. All right, get ready because this next concept is a total game changer. Everything we've talked about so far exists on this infinite number line that just goes on forever. But now, we're about to step into a completely different world, a world where numbers actually go in a circle. So just for a second, I want you to forget about infinity. Instead, just picture a regular old clock on the wall. You know how when you go past 12 on a clock, you don't go to 13 o'clock, right? You loop right back around to 1. Well, that's it. That's modular arithmetic. I like to call it clock math. We just pick a boundary, we call it the modulus, and as soon as our calculations hit that number, they wrap around and start all over again. It creates this finite, predictable, circular little universe for our numbers, which, it turns out, is unbelievably useful. So why is this clock math so important? What's the secret sauce? It's because it creates another one of these amazing one-way functions. Think about it. It's super easy to add, say, 5 hours to the clock and see where you land. But if I just tell you I ended up at 4 o'clock, well, it's really hard for you to know if I started at 1 and added 3, or if I started at 10 and added 6. See? Easy to go forward, hard to go backward. That is the key to scrambling data effectively. Okay, so let's take stock. We've got our prime numbers, we understand how they relate to each other, and we have our wild clock math system. Now, let's put all these pieces together and see how they build a real-world cryptographic tool. This right here is a substitution box, or an S-box for short. It's a fundamental part of so many encryption systems. And the idea behind it is actually pretty straightforward. A piece of data goes in one side, and a completely different, but totally predictable, piece of data comes out the other. Its entire job is to create confusion. So how does it work? Well, an S-box basically uses a secret lookup table. It's like a super complex decoder ring. The data that comes in tells it exactly where to look on the table, and the value it finds there becomes the output. But here's the thing. This process is designed to be totally nonlinear and unpredictable. And those mathematical properties we just talked about, especially modular arithmetic, they're used to build these tables in a way that makes the connection between the input and the output as messy and obscure as possible. So, let's do a quick recap of this whole journey. We started with the beautifully simple, indivisible nature of prime numbers and that awesome one-way property they have. Then we figured out how to understand the relationships using the greatest common divisor. After that, we jumped into the strange circular world of modular arithmetic. And finally, we saw how all of that gets combined to build real tools like S-boxes that swap data around to create total confusion. The whole thing, it's all built on pure number theory. You know, when you think about it, from simple primes to these incredibly complex ciphers, it's so clear that abstract ideas in math have very real, very powerful consequences. It really makes you wonder, doesn't it? The math that protects our entire digital world was once just a theoretical curiosity. What other hidden mathematical secrets are out there, just waiting to be discovered and change our world in ways we can't even begin to imagine?